then. So and again, I am going to have the chat up here. Okay, so you can unmute yourself and sort of participate. Here we go. So this was lecture 13. Which is 20th April today. So first things first. So it seems there is a test scheduled on the 27th, which is a week from now. I think that included more sections than I wanted to. So we are at 11.2. I still wanted to include like 11.5 there. So please wait on this one. I might just move it to Friday. Instead of next Monday. Does that work?
That's perfect.
Sure.
Okay. So I might just do it. The content I think will still be the same because I'm lagging behind. So let's move it to Friday. I'll put up the study guide as I usually do. And it will be the same like last time. So it will be in Canvas and you will have to upload it and all that sort of thing. Your final most probably is going to be in website. So no, Cecily, it's not this Friday. It is being moved from 27th to the Friday after. The only reason that I asked it was okay because there's not a lot of gap between your final and this thing then. So this happens to be on 1st of May and on the 16th you're taking the final. So let me think about this one. Maybe not Friday or Wednesday, but I'll move it. I don't know. Let me just see what I'm going to do. So please wait on this. And the reason I'm kind of discussing with you is if I move it to Friday, it's almost May 1st, and then 15 days you are going to take the final. So let me just think about this one. So maybe to Wednesday or something. So please wait on this. It may or may not happen on this day. So, but it will include chapter 8. And if it's going to happen on this day, then I'll have to not include the sections that are typed in there. So having said that, please wait on this. There will be a study guide on Canvas. But yes, it will be in Canvas and you will have to upload it and so on and so forth. So let's go ahead and get this thing going. And here we go. So we were talking about sequences in series. So sequence is just a list. It is denoted by AN, given by A1, A2, A3. Well, this is the first term, second term, third term, and so on and so forth. No trend, no responders for this one. So no, I'm not going there. I'm not going with the responders. So third term and so on and so forth. What is series? So series, just like I wrote here, the sequence is a list. Series is an infinite sum. So it is given by n equals 1 to infinity an, which means it is a1 plus a2 plus a3 and so on and so forth. So what is the question that we want to answer? We want to answer, does a series converge or diverge? What does converge even mean? Oh, we are saying that this infinite sum adds to a finite number. Diverge is, yes, infinite sum. Either we can not find it, which is does not exist, or it is infinity, which is not surprising at all. It's an infinite sum, so I'm not surprised it adds to infinity. So the question is, how do we do it? So how to determine, and here's where the game begins now. So how to determine if a given series is convergent. So that's the question. And we will start. So number one, compute Sn. Well, what is Sn? Sn is A1 plus A2 plus An. Somehow compute this. So this, if I have to write it, is the sum of first n terms. Then what do I do? I find limit as n approaches infinity of this Sn. If it is a finite number, the series converges. If it is infinite, oh, sorry, I'm going to write it the other way. If it does not exist, or it is plus or minus infinity, then the series diverges. Well, there's something more to this. If the limit is a finite number, we say the series converges. We also say that this one adds up to is the value of the limit. And that is when we say it's convergent. So the idea is, here is where it starts to get a little bizarre, because this Sn is not easy to find. In fact, you cannot find Sn for most of them. So at this point, I want to say to you, I can't read your chats because the Zoom is behaving a little bit funny. It's on my other device. So I'm thinking you can still see the screen and you can hear me.
Yep.
Okay, thank you, Russell. So this Sn is not easy to find. So what do we do? So we start to look at the type of the series. So number two, I'm going to see if it's a geometric series. So what is a geometric series then? So now it is back up and I don't know why it's doing that. So and I'm trying to get the chat window up. So here it goes. So remind me, all of you, how do you determine a series is a geometric series? What are the two components you need? Very good. What is A, Joshua?
A being the first term.
Very good, sir. A is the first term of the series. And R, go on.
R is the common ratio.
And how do you find the common ratio?
The second term over the first term.
Very good. So second over the first, third over the second, all of these ratios should be the same number R, and it's a geometric series. So if it's a geometric series, then it is quick to say if it's convergent or divergent. And that is why I'm going to digress a bit. And I'm going to say every time it's given series, I will write out its terms. So if it's a geometric series, then if the absolute value of R is less than 1, we say it converges. If the absolute value of R is greater than or equal to 1, we say that the series diverges. So I want you to tell me any questions about this one.
So maybe I was misunderstanding. A geometric series is not necessarily just a raised to the exponential.
Not necessarily that. Let me take an example right away. So here is my first example and see what you mean by that. Most of the times you will find the reciprocal, a to the power of n because of that common ratio. So I'm just going to take this one and see if you like this, which is n equals 1 to infinity, pi to the n over 3 to the n plus 1. So I want all of you to take this and start writing the series out. And this is me preparing you for the test. So number one, I want you to write out the first few terms. Which means what? I'm just going to say, oh, this is pi to the 1 over 3 to the 1 plus 1 plus pi squared 3 to the 2 plus 1 plus pi cubed 3 to the 3 plus 1. So if you want to write it correctly, you can say this is the first step. And I just want to say that on the test, when you're going to take either Monday or Friday, this is going to count. So just writing out the series is going to be part of your partial credit. So you wrote out the series. And remember, on the test, I'm not going to tell you whether this is geometric or not. It's your job to determine, meaning you're going to look at the series and you're going to say, okay, so the first question, is this geometric series? And if it is, I want two things from you. I want A and I want R.
Are you asking for that right now, or?
Yeah.
Ah. So A appears to be pi over 3. Am I right on that?
A is the first term.
So are you saying A would be pi over 3 squared?
There you go.
Ah.
And the common ratio? Remember, it is this over this, and this over this, and so on and so forth. Very good, Cecily. Pi over 3. So this is a geometric series because you found this to be common ratio. And now you're just focusing on this one. So tell me, absolute value of pi over 3, is this less than 1 or greater than 1?
Greater than 1.
Answer, go ahead, Russell. The verdict is this series
Diverges.
very good.
And that's... Sorry, go ahead.
No, I was just going to ask you, did it answer your question? So I was going to talk to you. Did this clarify as to what you were getting to?
I think so. I'm going to have to work on it on my own. It's just... Do all geometric series have exponents? I think is my question.
To that, my answer was yes, most of them will do because of this common ratio thing. So, but I'm just going to say this, but every exponential series is not going to be necessarily geometric. And what do I mean by that is very simply this, that if I give you this one, See, it has your exponents, right?
Mm-hmm.
So go ahead and write the series out for me. This is going to be what?
1 over 1 squared, 1 over 2 squared, 1 over 3 squared.
And so you tell me, is this geometric now? Because this is 1 plus 1/4, 1/9, 1/16.
No.
And there it is. That is what I was trying to get at. So do not generalize. Just because you see an exponent doesn't make it geometric series. What makes it a geometric series is exponent or not. When you have the next term over the previous, the next over the previous, this should be a constant, the common ratio.
I see. That answers my question. Thank you.
No worries. So this is what I was trying to get at. So our story continues. So what if it is not a geometric series, like this one? And today I want many of you to participate, again, because this is very conceptual. This is what I would have done in the classroom anyways. So what if it is not a geometric series? So what are your two problems? That you, Sn, for example, look at this, the thing I put up here. What would Sn be? Oh, Sn be 1 plus 1/4, 1/9, 1/16 plus 1 over n squared. So how do you even find Sn? Are you going to do the LCD of all of that and just find Sn? It's just too much. So now the thing is there an easier way to say if this geometric series converges? And at this point, I want everybody to stop writing. As I used to say in the class, drop your pencils. So literally drop your pencils, stop writing, and look at this very, very conceptually. Remember, what is series? You're adding all these terms together. So I want you to stay away from these terms, and I want to look at this one. So this is your series. You're adding all these terms together. So my question to you is, if, and this is a big if this sum, if this infinite sum has to converge, and let's look at conceptually, what does it even mean? You're saying that this infinite amount of terms that you are adding add up to a finite number. So I'm going to say this, and you're going to tell me if you agree or disagree with the statement. And I'm saying, if this series has to converge, then what must happen? That when I start adding these terms, after a certain amount of time, the terms that come after should be negligible. Meaning, what am I saying? That maybe when I'm adding this infinite term, I add up the 1,000 terms. I don't care how many terms I have to add, 10,000 terms, or maybe 100,000 terms. I add those terms, but the terms that, and I get some number when I add these many number of terms, I get that little s. But what should happen if that s has to stay a constant? All the terms that come after, meaning the 1,001th term and after, the 10,000 in the first term and after, tell me, if this s has to stay in place, if it doesn't have to change, what should happen to the terms that come after your s or after this sum? So again, let me put it this nicely. So you are trying to add infinite terms. Let's say you have added 1,000 terms here, and you've gotten a number s. If that s does not need to change, what should happen? As you are adding terms after the 1,000 term, what should happen to these terms?
They won't make much or any difference to S.
Very good, sir. If they won't make much or any difference, then these terms should almost be zero. Right? That's your translation, isn't it? That when you start adding the 1,001 terms, that means eventually these terms should go to zero. Well, what happens if they don't go to zero? Let's say if these terms go to 3, what does that mean? Oh, you have added the 1,000 terms, which is S, and after that you are adding what? 3 and 3 and 3 and 3. What do you think is going to happen to that sum? Is it going to converge?
No.
Very good, sir. So here we go. So now we are saying, what if it is not a geometric series? Then the idea is, I'm going to erase all of this. And then the idea is let's look at, actually, I'm going to let it stay there. So then the idea is, let us look at the behavior of nth term an. If limit as n approaches infinity, an is not zero, or it does not exist, meaning it falls into this category, which is like it's 3, 3, 3, then what would happen? Then you agreed with me, then the series diverges. So the question is, but what if length, the limit is actually 0? In principle, we agreed that the series converges. In practicality, you will notice that this is inconclusive, meaning I'm going to show you a series where this limit is equal to 0, but this one series converges, the other one does not. So I'm just going to say this, that this, what I wrote up there, is the test of divergence. So here we go. So I'm going to go all the way up there and say, series is an infinite sum. We wanted to know if the series converges or diverges. First, compute Sn. Find the limit of Sn. That's one way to go. But Sn is not easy to find. So one of the ways to get around that Sn is to identify if it's a geometric series. If it's a geometric series, job done. It's easily done. What if it turns out to be a series like this, which is not a geometric series? Then what do I do? Then you apply something called the test of divergence. So here we go. So what if it is not a geometric series? Then you have more ways to go, which is the test of divergence. So what is this test of divergence? Compute the limit n approaches infinity an. Notice that this is the nth term of the sequence. I'm going to give you an example very, very soon. If this is not 0 or does not exist, we say that the series diverges. If it is equal to 0, it is inconclusive. In other words, the test fails. Why? We will be able to see that one today. So, this is what, as it says, is test of divergence. So what is my pet peeve? Please do not write by test of divergence, the series converges. There's nothing like that. You're testing for divergence. You're testing if I have diabetes. So don't tell me I have some other condition which I haven't even tested for. So I don't have diabetes, by the way, but I'm just saying. So it's a test of divergence, which means you're testing for divergence. So just tell me that by test of divergence, the series diverges. Please do not say by test of divergence, there is some other condition that you have identified with the series. So questions then, I'll be okay. And here is an example coming up. So should we go for an example then?
Yes, please.
And I'm going to get something that you already know. So here we go. So here's an example. So number 1, write out the series. So this is going to be tan inverse 1 plus tan inverse 2 plus tan inverse 3. Look at the series in many different ways. So if you have a calculator right now, or if you are on your computer, go to Desmos and graph that tan inverse n. And if you graph that tan inverse n, it should look something like that. And what we are talking about, remember, a series is you are just adding this tan inverse 1 plus tan inverse 2 plus tan inverse 3. So these are the light bulbs. These are your Christmas lights. It's not the wire you're interested in, it's the Christmas lights, and you are just adding these terms. So far, so good.
Yes.
Remember, you're adding these terms. So I'm just going to get you a play with that. So I'm just going to say that these light bulbs themselves, these Christmas lights, are a sequence. When you start adding them together, it becomes a series. Remember extreme couponing. When you're putting these light bulbs in your cart, it's a sequence. When you are adding all of those at the checkout, it's a series. So we want to know whether the series converges or diverges. So let's start out first. So what would Sn be? Oh, Sn would be tan inverse 1 plus tan inverse 2 plus tan inverse 3 plus tan inverse n. I have no idea what it adds up to. Meaning what? I'm just going to go the screen up a little bit and I'm going to say that option number 1 is out. So I can't do this. So far, so good, people.
So why is option 1 out? Because we can't find the...
Because can you add and tell me, Russell, what this one would be? What is tan inverse 1 plus tan inverse 2 plus tan inverse n?
No,
Very good. What am I going for? I could compute when Sn was 1 plus 2 plus 3 plus n because I knew this formula from discrete math. So I could tell you what this element or what these terms added to, but I don't know what these terms add up to. So I cannot compute Sn, so I cannot take limit of Sn and so on and so forth, and that is why that option is out. And I want everybody there. So I'll be okay there. Do we understand that? And remember, you can click yes in your participant. If you click on the participant, you have like a yes button, so or you are going to type it in. And so there we go. Balneet says yes. So I want it from all of you. So Sam, Vincent, so I have 4 yeses. I have 28 people. I'm waiting. There we go.
so maybe I'm misunderstanding this. Like, if we start inputting numbers, tan inverse 1, tan inverse 2, like we can get decimals and we can start adding those together.
Right, but I'm talking about the last one. What about the last one? How would you do tan inverse n?
I mean,
Because remember, this one, 1 plus 2 plus 3 up to n, was the sum of first n terms. But as I said, discrete math gave me the formula n plus 1 over 2. I don't have any such formula for this one.
got it.
Okay, so I'm going to erase that. So option number 1 is out. So let's look at option number 2. And this is where what you said earlier makes great difference here. So is this a geometric series? Meaning what? You have the calculator with you. So go tan inverse 2 over tan inverse 1. Go tan inverse 3 over tan inverse 1. And do you get the common ratio? So this over this over this. Does it give you a common ratio? And does it? So do that and let me know if it gives you a common ratio. I can't see your chats again, so please speak up.
It does not.
Very good. So it says this one is not a geometric series. And this is what you will do on the next test for me. So I will give you a series and you will have to determine whether it's convergent or divergent, meaning you are going to have a cheat sheet. You know, it's an open notes, but you are going to go through this thought process, which is number 1, write down the series, get an idea of what the terms look like, and then you are going to sort of check this one out, that can I find Sn here? The answer was no, you can't find Sn. Is it a geometric series? The answer is no again. It's not a geometric series. So how do I determine whether this converges or diverges? I'm going to go to the test of divergence, meaning I am going to compute the limit of this one. So I'm going to compute limit as n approaches infinity, tan inverse of n. If you have graphed that function on your calculator, tell me what this limit is.
It's going to be 1 if I recall.
So you have graphed this on your calculator, right? So tell me what this line is.
I'm just trying to recall it, but
I know you are, but I'm asking the others as well. So what is limit as n approaches infinity tan inverse n? And I'm waiting for somebody to type it in the chat or say. And now, Aaron, it's not going to be 1. So we did this limit as n approaches infinity, tan inverse n is
2.
no, and
No.
it is really. And for that, for all of you, because there's that silence there, and I don't like it at all, because it is, no, this is not a guessing game, everybody. So because I'm getting all sorts of answers, and I'm thinking, no, you're not thinking right for me. So I'm just going to say that tan x is this, right? Which is what? As x approaches pi over 2, y approaches, x approaches pi over 2, y approaches infinity. This is tan x we are talking about. What happens when you take an inverse? You swap them, don't you? Very good. So the answer is pi over 2. There we go. And William, you were right. So the answer is pi over 2. So tan inverse n is pi over 2, meaning where are we? Your limit is not 0, so the series diverges. So you're going to say by test of divergence. The limit is non-zero, so the series diverges. For all of you, I have this question. What about the sequence, though? What about this one? What about this list? Remember, we're not adding them now. We are just looking at the behavior of these terms as you reach infinity. So what about the sequence? Does that converge or diverge?
Converge?
Very good. It converges. Why? Because as you follow it to eternity, all the terms will start looking like what? Pi over 2. Meaning, if you have graphed these terms, then all your Christmas bulbs, light bulbs, are going to approach that line pi over 2. They're never going to cross it. Your Christmas lights are never going to go into the neighbor's yard. It's going to stay, and it's going to be pi over 2. So I just want to say that when you find the limit like that, you will find that the sequence converges, but the series diverges. So is there a connection? Nothing at all. So a convergent series sequence might get you divergent series. A divergent sequence might get you convergent series. So there's no connection at all. What I wanted to emphasize was, look, the same limit gives you two different verdicts depending on which entity you're talking about. Are you talking about sequences or you're talking about series? So I'm going to continue this. I want to make this connection. So let's say you have been given a series. I'm going to repeat myself. Series is what? A1 plus A2 plus A3. I'm going to say over and over and over again that when I say I have given you a series, you should think, oh, she's giving us an infinite sum. The question is always going to be, does this converges or diverges? The question is, how do you go about it? Number one, find Sn. Not easy. Number two, geometry. But not all series are geometric. Number three, oh, I have the test of divergence. But remember, the test of divergence fails when the limit is 0. And then what do I do? And here is a series for you, which I think should look familiar and you should like it. So here is a series. We are always going to write it out. And when I say write it out, I like to write it out 1 times 1 plus 1 plus 1 times, and please write it with me. If you need me to pause, let me know. So I'm saying this is that series. If you're wondering why I'm not multiplying, it's for a reason, but I'm just going to say, oh, this is that series. So this is the series that you're talking about. You want to know if this infinite sum converges or diverges. So far, so good, people. And I'm going to pause, wait for you to catch up. Are we all right there? Russell just took his yes away. And does that mean something, Russell?
I took it away and put it back. But
Okay. I cleared all of you again. So start the thought process for me. Number one, can you find Sn? Which is what? Plus 6 plus 1 over 12 all the way. And I'm going to quickly say, no, I don't even want to go there. It's not easy. So let me look at the geometrics. So is this series geometric? Meaning this over this over this. Do you get the common ratio? And so is this a geometric series? Very good. No. So it's not a geometric series because it's not common ratio. So what is the next thing left for you to do? A test of divergence. Because you're going to go through all the steps. So the test of divergence says take the limit of, and I'm just going to say ignore this, and I just take the limits of this one. So if I take the limit of this one, what do I get? Limit as n approaches infinity of 1 over n times n plus 1 is going to be very good. And this is going to be 0. So what happened there? Oh, the test of divergence fails you. You cannot say whether it converges or diverges. That means what? We have to do something else. But this is what we do. And I want everybody to completely stop writing. And I want to say, oh, but you know what? That 1 over n times n plus 1, it brings me back memories. This looks like partial fractions. So I should be able to write this as a over n plus b over n plus 1. So in other words, summation n equals 1 to infinity 1 over n times n plus 1 is summation 1 to infinity a over n plus b over n plus 1. Take a minute, and this time I want answers from all of you. And this is what I'm going to do. I'm going to let you compute the values. I want the values of A and B. You've already done this before. And when I say 3, 2, 1 and type, I want everybody to type into this format for me. A equals what? And B equals what? So I'm going to give you a couple of minutes. You know this thing. It's from partial fractions. So in 2 minutes, I'm going to ask you to type. And when I say type, I want everybody to type it together. So ready for this thing? So take a couple of minutes. Get the values of A and B for me. How do we get that? Partial fractions. You've done this before. And yes, the cover-up method. And here we go. 3, 2, 1, type. So I want A equals and I want B equals. Nicely done, people. So A equals 1, B equals -1. You're absolutely right. So I'm going to write that this series is n equals 1 to infinity, 1 over n minus 1 over n plus 1. And now Sn just looks very, very interesting. So Sn would be 1 minus half. Oh, this is n equals 1 plus half minus 1/3. This is n equals 2 plus 1/3 minus a quarter, which is n equals 3. And so on and so forth. I would get 1 over n minus 1 over n plus 1. This is Sn, correct? It is the sum of first n terms, so I have to go from 1 to n. And so what happens then? Look, this gets cancelled. This gets cancelled. So tell me, what am I left with? So Sn will be what in this case?
One.
Very good. So it's going to be not plus, Jezebel. You're just missing that. It'll be 1 minus 1 over n plus 1. Right? You're right. You're okay. So this time I could find Sn and this kind of series. How do I know which relates to partial fraction? It's called a telescoping series. So when I have telescoping series, I have found Sn. So I'm going to take limit as n approaches infinity of Sn, which is limit as n approaches infinity of 1 minus 1 over n plus 1. And now you will notice, Russell, how you were right. So when you take this limit, what is the answer to this limit? Very good. And Russell was right there. The limiting value is 1. And so what are you saying? Oh, you are saying that these, if you add them, these ones, this infinite sum, 3 times 4 and so on and so forth, if you add them, they just add up to 1. So this series converges. Not only that, we are saying that this infinite sum, n equals 1 to infinity, 1 over n times n plus 1 is 1. I'm going to give you a couple of minutes. I want everybody to stop writing. And I want to explain this term. Why is it called a telescoping series? So, ready then? Or should I wait for somebody there? Oh, yes. Yes, Jezebel, if you've done discrete math, then you see the connections. And this is discrete right now, what we are doing here, because we are not dealing with continuous functions. but we are going to jump back to that continuous part of it. But right now, this is discrete because you are only talking about those light bulbs. But in calculus, we talk about the wire as well. So these are the discrete objects. And I'm just talking to you, Jessica, because you've taken that one. So these are the discrete structures. These are the objects that make up discrete math. So all of you ready for this one? Why is it called a telescoping series? And I'm just going to say this, that the reason it's called a telescoping series is really, have you seen a sailor's telescope? For that, I'm asking you, have you watched Pirates of Caribbean?
Yes.
Okay. There we go. Very good. So in Pirates of Caribbean, he has, if you, what is it? Captain Sparrow? Jack Sparrow. Yeah. So he's got a telescope, and when he's looking for land, that telescope goes, he expands it, and then he pulls it back. So that expansion is this, you're finding Sn. And look, after the terms cancel, that is you pulling it back, and you are just left with this much of a telescope, right? Because he puts it back and puts it in his coat pocket. So that is why it's called the telescoping series, because when you expand it, what do we mean by expand it? Write out all the terms. That is you with Jack Sparrow current looking for land, so it's expanded. And then when you cancel all the terms, then yes, you've seen land or whatever, and you've put it back in the pocket, and that is why it's called a telescoping series. So now we are added one more twist to it, that if it's a telescoping series, how do I identify it's a telescoping series? Oh, because you are going to have something like a partial fraction. So now here is another example, which is going to really, really psych you out. But I like to teach this with this example. This is my...
Can I ask a quick question?
Sure.
So we expand it, we start canceling out terms. Why, when we reduce it down, do we lose the n? Because it starts out as 1 over n minus 1 over n plus 1. Why do we then come down and get 1 minus 1 over n plus 1?
Oh, that is because first thing, you are skipping a step here. You wrote this as partial fractions. So you're missing the critical step here. So you wrote this as partial fractions, and you're saying that this series is this. Well, if it is Sn, then you're going to go n equals 1, n equals 2, n equals 3, n equals n. Maybe I should have written it I equals 1 to infinity. And then I could have said, oh, I is 1, I is 2, I is 3, and here I is n. So Sn is you adding n terms. And when you add n terms, Russell, these two terms do not cancel because they don't have anybody to cancel with.
I think I'm starting to understand.
Okay, because notice the pattern. The next one, half, cancels with the half before, third cancels with the third before. But this one doesn't have anybody here to cancel it, but this one will cancel because when I equals n minus 1, this is going to be 1 over n minus 1 minus 1 over n. And this gets cancelled.
Got ya.
And so the sum just turns out to be this. There we go. Yeah, Cicely was right there. And so the series converges. So if it is a telescoping series, but for us, how are we going to know if it's a telescoping series? Or we're going to relate it to what we've done before, which is partial fractions, which means here is my next example. You are going to work it out, and you're going to tell me, how will you do this series? And
take it to the...
Go on, yeah.
Oh, I was going to say take it to the nearest math major, but...
So I'm just going to say this because it's a series. And we don't need a math major, Russell, because you will see when you write it out, you will see what I'm saying. So if I write it out, what do I get? I get 1 over e plus 1 over 1 times 2 plus 1 over e squared plus 1 over 2 times 3. And the reason I picked this example is, why do I ask you to write it out? Because then people start taking shortcuts for no reason at all. When it is such an easy thing to do, all I'm asking you is to write it out. Plus 1 over n times n plus 1 plus, because that is what that series is, correct? So we are just going to write it out. So far, so good, people. And this is all addition. So can I group them? And I'm just going to group them. I'm going to say, isn't this the same as 1 over e plus 1 over e squared plus 1 over e cubed? This plus 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 and da 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 da. Agreed. Because it's the same thing, isn't it?
Yeah.
And now tell me, this series, you already know it converges. Not only that, you know these terms add up to 1. Can you tell me, what about this one? What does this one add up to?
Isn't
So
that
take-
one geometric?
Very good, sir. So the first term is what?
1 over e.
Very good. Keep going. The common ratio is
1 over e.
okay. And so, of course, you're going to say, okay, 1 over e is less than 1. It converges. We got that. Adds up to what, Russell? This infinite sum, if it's a geometric series, adds up to what?
That I don't know.
Does anybody remember the formula? It adds up to what? Because we did this last time. So geometric series, if it converges, very good, Trent, it adds up to a over 1 minus r. So I'm going to say this adds up to 1 over e, 1 minus 1 over e. So I'm going to say this adds up to 1 over e, e minus 1 over e. So this adds up to 1 over e minus 1. So the entire series, I'm going to go back to the problem. Not only that I know it converges, I can also tell you what it adds up to. It adds up to 1 over e minus 1 plus 1. And that's going to be e over e minus 1. That is what that series adds up to. So I'm going to pause here and questions.
You had me until you rewrote it. How does it go from 1 over e minus 1 plus 1 to e over e minus 1?
This is just e minus 1 over e minus 1. And then they have the same denominator. So just add the numerators and you have that.
Ah,
Yeah. That's the oldest trick. See, we have been going through these tricks. When it is 1, I always take this denominator and write it and quickly do it. If not, you can do your LCD, which was e minus 1, which is the same thing, really. This is just a quick, a cheeky way of sort of looking at it. So questions, people. And I'm going to call out people. I don't hear my favorite people anymore. Nara doesn't talk to me anymore.
What do you mean?
Ah, there you go. I just let you hear your voice, even if it says, I have no idea what the heck you're saying. But so are we okay there, Nara?
Would it be possible if you could just scroll down just a little bit?
There we go. See, you could have just said that. It makes me happy. And my other favorite people, which is Vincent, Jivu, Sam, because Trent, Bhavneet, Karan, they still talk to me. Jonathan, I haven't heard from Jonathan in a long, long time. Joshua talks to me. So I'm just looking at the list of participants till Nara gives us an okay to move forward. Sadhna doesn't talk to me anymore. Almari, Amir types in a little. Cecily talks to me. Ilian, no. Ivan has stopped talking altogether. Long has lost interest. Missile, Niandy. It doesn't matter, Karan. You're still talking to me. It doesn't matter whether you say Pirates of Caribbean. Pirates of Caribbean was a very important part of understanding what a telescoping series is. Savannah doesn't talk to me. Tiffany doesn't. William does. So, Sadhna, did you type anything? Because you've stopped talking to me altogether. Okay, Sadhna has not typed in anything. See, she doesn't like me anymore. I'm very sensitive about these things. Oh, there you go. Okay. Okay, so Aaron's question was how is converges equals 1, because look at the previous example. That was the previous example, and now my screen is stuck. Oh, there we go. So, Aaron, for your question, I'm just going to say look at your notes here. So, Aaron, you are going to... Oh, you could type long. You could just say that, Mrs. B, I've learned all of this. You're not teaching me anything new, or whatever the case may be. So I'm just kidding anyway. So Aaron, this is how we knew that this added up to 1. And that's how I made the example anyways, because I didn't want to work again through it. So I'm going to start. I'm a queen of repeating, so I'm going to repeat over and over and over again as people claim it's, that you're listening. So here it goes. So when I ask you that I'm giving you a series, you should say to yourself, now look at what I'm trying to do. I'm trying to shape your thoughts, which makes me closer to some of the groups that we shouldn't be talking about. So I'm trying to program your thoughts. So this is like the Manchurian candidate. So when I say I'm giving you a series, translation, you should be thinking, oh, she's giving us an infinite sum. The question, does this infinite sum converge or diverge? Converge meaning, is this infinite sum finite? Diverge, it is infinity or does not exist. So if it diverges, I'm just going to say we are not very much interested in this one, but we are interested in separating them. I want to know, if you throw a series at me, I want to know, to be able to quickly tell you whether it converges or diverges. Because if it converges, then I know it adds up to some finite number, and I want to find that finite number. I want to find the sum. So let's run through that again. So if it is a geometric series, then can I find that sum? Yes, it is a over 1 minus r. If it is a telescoping series, then can I find that sum? Yes, it is the limiting value of Sn. It is the limit. The sum is the limit. If it is neither of those, which means what? I'm just going to throw that series in there again, tan inverse n. For example, I know it was not converging, but that one diverges. What did we use? We used test of divergence, which I'm going to say T of D. So T of D is test of divergence. So for us, I'm going to go ahead and do this. But remember, test of divergence never tells you convergence anyways. So test of divergence just gives you one word, that it diverges. It never tells you whether a series converges. But again, why do we use this test of divergence then? Then we can quickly tell the girl that we are not interested. So all of you boys there, if you're going to go on that, or the girls too, if you're going to go on the Bachelor or Bachelorette, then you quickly know who not to give the rose to. Because you've separated it. They're not even the list. They're not even the possible candidates. So test of divergence just tells you not interested really, really quickly. Maybe it's the crooked teeth. I don't know. Maybe it's the wicked smile. Right? These are bad jokes, people. Thank you, Russell. Thank you for that little bit of, because I'm looking at the screen. Nobody seems to be saying anything. So either you have no idea what I'm talking about, or you are in deep thought about who to give the rose to. Again, a bad joke. So there we go, Karen. That's what I thought. So anyway, so we are here. We are at the test of divergence. And now we are looking at this thing, which is, oh, but what about the test of divergence? You know, if the limit is, when I'm using T of D, and the limit turns out to be 0, it says it was inconclusive. That means, if you want to quickly know where it was inconclusive, I'm just going to give you this example. A 1 over n times n plus 1, this was a telescoping series, so you could do it. But if I just give you the very simple one, which is this is called a harmonic series, by the way. What do I want to point out here? That if you write out this series, number one, you can't find Sn. It is not geometric. It is not telescoping. And T of D fails you. Why? Because limit as n approaches infinity, 1 over n is 0. And T of D says that the limit, if it is not 0 or does not exist, it converges. So we are stuck. So if we have a series like this, then how do we determine whether it's convergent or divergent? And for that, again, I want you to completely stop writing. And we are going to look at something called the integral test. So what is an integral test? I'm going to write the comment. It connects improper integrals, which you've already done, to infinite series. And how does it do that? And I'm going to write the integral test. By the way, all these tests are going to be with you. Even if this was a regular semester, we would have been in the classroom, then I'm going to put up a document, a cheat sheet, which people were using in the previous semesters when they're doing this integral test. So I'm going to write this integral test, which is in the book. So this integral test says what? And there are components to it. And because you are going to use a cheat sheet, you're going to be very, very detailed in when you answer the next test. So suppose f is continuous, positive, and decreasing function on 1 to infinity. I'm going to give you an example very, very soon. Just kind of start writing this with me. And we let, so here is number 1. Suppose f is number 1, continuous, positive, decreasing. Let an equals f at n. Then we say that n is convergent if and only if, this is for you, Jezebel, this is for your discrete, if and only if the integral is convergent. And it is divergent if the integral is divergent. So I'm just going to write this in my words, which is, suppose f is continuous, positive, decreasing on 1 to infinity. We have an equals f of n, then I'm just going to say as the integral goes, as the improper integral goes, so goes the series. So let me work out an example. And at this point, I want everybody done with the writing and everybody ready for this example. So I want to go up again. I'm going to work this one. Remember this series, this harmonic series. It is not geometric. It's not telescoping. T of D fails you. So everything that you had before, all your tools do not answer the question whether this converges or diverges. So we are going to go to a new tool, which is integral test, which we have done. We've done improper integrals before. And now it's time to connect the concepts. So I just want from each and every one of you, ready? Because I do want to finish this. And it's not going to be that bad. So here we go. So we've already written that. So the series is n equals 1 to infinity 1 over n, which we know is 1 plus half plus 1/3 and so on and so forth. So when I work this, I like to do this a little bit differently. So number 1 is really number 2, which is I find a corresponding function. So tell me, what would be the corresponding function here? In other words, these are your Christmas lights. Tell me, how would the wire run? So the corresponding function which these Christmas lights are on, do you agree it is 1 over x? In other words, this is your 1 over x. These are your Christmas lights. This is 1, this is half, this is 1/3, this is... And you're trying to see what they add up to. So here we start. N goes from 1 to infinity. So I'm going to say, okay, f at n is 1 over n. And n is what? Greater than or equal to 1. So number 1, is f continuous? So number 1, I'm going to say f is continuous. Why? Because n is greater than or equal to 1. Where does it have a discontinuity? It has a discontinuity at x equals 0, but we are not even talking about x equals 0. N is just greater than or equal to 1. Well, if it is positive because of the same reason, n is greater than or equal to 1. What about decreasing? Now I'm going to say for decreasing, we're going to use derivatives. So f prime x is equals negative 1 over x squared, which is always negative for x greater than or equal to 1. Remember, x and n, they are the same thing. So f is decreasing. So what does the integral test really say to you? It's saying follow the wire. If this converges, if this function is this improper integral, so you are going to get the corresponding improper integral, which is 1 over x dx. If this converges, then your series converges. If this diverges, the series diverges. So tell me, does this converge or diverge? And for that, I'm going to ask you to remember this one. We did this in improper integrals. So what did we say? This converges for P. So I'm going to wait for you to join me. So this is from improper integrals. I'm going to put it in a box. So I'm going to say recall. I don't even need to compute this one. So silly, the derivative, because how would you know f is decreasing? Very good. That it converges, current for p greater than 1, it converges. P less than or equal to 1, this diverges. So this integral, I know, diverges. So by integral test, the series diverges. So I'm going to start with Intego test. I'm falling a little bit behind, as I know my updated calendar. I think I'm not sticking to that even because I think as we go here online with all these technical issues and everything coming up and me waiting for your response, it's slowing me down. So I do want to stop here because I know you have other classes to go to, but this is the start of that Intego test. So good news for you, I'm not going to give you any new homework today. I'm just going to assign it on Wednesday.
Thank you.
Probably I'm going to move this, but this is the idea where, you know, your improper integrals kind of go to the series. But the homework today is due tonight. So finish that homework, take a break, but please kind of look over the notes because I want you to be ready and answering me faster than you have been doing. I know this has been hard. Let's get this. And yeah.